Okay, so we introduced the idea of ageostrophic flow when there is friction that cannot be ignored, and we had seen this section from 20 north to 70 north at 80 west, which we used to show the relation between the temperature gradients dt dy and the geostrophic shear, right? So you can see depending on the sign of the temperature gradient, you get u that is varying from the surface to the upper atmosphere, and the relation really is dt dy to du dp, right? The pressure coordinate that we have here. So we are looking at geostrophic shear and dt dy, the temperature gradient. Now let's look at the same. So that previous figure is shown as a section along this line, and now look at this surface pressure field and surface wind at some time, particular time on June 21, 2003, which is what we have been looking at. It's the same time as the upper level flow we have been looking at in previous figures. Here the pressure contours are in 4 millibars, and one full quiver represents a 10 meter per second and half a quiver. So you have a quiver here, for example, wind vector here. So you have a quiver which is 10 meter per second, and it's pointing, wind would be flowing away from the quiver, right? So 10 meter per second, 10 meter per second, this is less than 10 meter per second, and so on and so forth. If you have more than one quiver, then the wind speeds are greater than 10 meter per second. We have already seen this, but we have now shown a blown up figure with lots of pressure lows and highs. So this is a low, low, high, low, high. So this is a good way to see where the ageostrophic flows happen, right? So when you have high pressure, you call it a high. When you have low pressure, you call it a low. And obviously you get cyclonic circulation or counterclockwise circulation around a low in the northern hemisphere where we are, and a clockwise flow around a high, as we have already seen many times before. But you can see that the flow is generally crossing the pressure lines in many places. We are at the surface because obviously we are looking for friction induced sub-geostrophic flow, as we call it, right? Near the surface, obviously friction is important, cannot be ignored. So we are at the surface, so we will see how the flow lows and highs are created, but right now we will just go to a simple model of the winds in the Ekman layer. Just to repeat the point, in case I didn't say it before, I think I have. When you have cyclonic flow, then you have convergence, then you have to have vertical motion upward, whereas around the high you have divergence, so you have subsidence or sinking motion. We will see that as well, right? So going to our equation of friction with the balance between Coriolis and pressure gradient, but in the presence of friction. So if this is 0, obviously we would recover our geostrophic balance. So assuming that x-axis is directed along isobars, so we're going to derive something very simple just as an illustration, and that the surface stress drops exponentially over some boundary layer z over delta, right? As the winds from the free atmosphere come down near the surface, they have to go to 0 at the surface, right? So unless you're on the ocean, water can flow So in fact you get currents modifying the interaction between the atmosphere and the ocean, and the friction tends to be less because ground, which doesn't move, offers more friction, and it depends on whether it's vegetation or hard ground and so on and so forth. Nonetheless, let's write friction as a simple drag coefficient divided by the height of this boundary layer we are defining times u. So friction is proportional to the velocity, as we can expect, and it's proportional to the drag coefficient of the surface property that's being used here, and the boundary layer height. It's minus k over delta u because friction is always in the opposite direction to the direction of motion u, right? So we plug it into this equation and get our components along x and y. So in the x direction you have minus f v equals minus k u over delta. This is the friction in the x direction. F times u plus 1 over rho dp dy. Because pressure we have aligned along x, there is dp dx is going to go to 0. Constant pressure line along x, right? Or x points in the direction of pressure. So dp dx will be 0. So you have f times u plus 1 over dp dy equals minus k v over delta, where v is the meridional velocity. So v is entirely ageostrophic in this simple construction we have made. So minus fv is just friction. So there is no impact of Coriolis on this component, okay, because the dp dx term has gone to 0. So it is entirely ageostrophic, and u can be written as 1 over minus 1 over 1 plus k squared over f squared delta square 1 over rho f dp dy. Don't worry about the particular form because this is just a idealized simple example to show that there are dependencies on drag coefficient and the boundary layer height as well as rotation, okay, in the u direction because of the choice we made for the x-axis. And the ratio of v over u is k over f delta. What is the point? This is to show that u is weaker than its geostrophic value, because geostrophic value would be just this, but we are dividing by a number that's greater than 1. K squared or f squared delta squared is a positive quantity, so dividing 1 by 1 plus something is going to give you a fraction of the geostrophic value. So friction is weakening the geostrophic current, so we have sub-geostrophic flow. If u is greater than 0, then v is greater than 0 because of this relation between v and u, and if u is less than 0, then v is less than 0. What does it tell us? Basically it tells us that you expect the in a geostrophic balance that is only modified by friction, you expect a relation between u and v, and there has to be still a dependence on f, and just because of the way we defined friction, we have created this term here, but nonetheless you create sub-geostrophic flows. The additional term to remember is that k, the drag coefficient, is going to be higher on land, where the wind is literally being there is a brake put by the land on the winds, whereas on the ocean, as the winds blow on the ocean, the water can move, and they do often move, and the friction is reduced. So you have to take the difference between the ocean currents and the surface winds to do these same calculations. That's just a simple example. So let's look at the vertical motion induced by this Ekman layer delta we defined. So general definition of Ekman layer is this friction layer over which momentum is being transferred, either from the atmosphere to the ocean or from the land to the atmosphere. So writing again in our pressure coordinate the continuity equation or the mass balance. Remember, we had taken out rho by using the pressure coordinate, which made the continuity equation look almost the same as the incompressible flow, except in the incompressible flow you have vertical velocity and dz. Here we have d omega dp, where omega is the velocity in the pressure coordinate. It's not vertical, it's normal to the constant pressure lines. Okay, so we can write this as grad p of grad p dot u ageostrophic plus the omega dp equal to 0, because we are in the Ekman layer and the velocities are ageostrophic. So essentially what ends up happening is, when you have a low pressure, as we saw in the surface pressure chart, we said we have counterclockwise flow, you have convergence, so you have flow, upward flow. Okay, so there is flow into the low inducing rising motion. This is essentially what happens when we were talking about convection, right? Air was warming up and air was rising, and there was convergence of air to replace the rising air, and that convergence, when it happens near the surface, there is friction. So that low that is created, it has got a cyclonic flow around it, whereas in the subtropical gyre, for example, we had subsidence, divergence, and we had clockwise flow of the trade winds and the westerlies. Obviously, I'm mixing up scales. These are, let's say, smaller scales as the pressure chart we saw, but this works at all scales, obviously, right? So there is our Ekman layer. Okay, that's the basic concept of ageostrophic flow in the atmosphere. Obviously, you can find it in many places, but it's easier to look at the surface. You can also look it at, find it at where the wind hits the mountains or hits the ocean. There are other friction forms which we are not looking at here. Okay, so that's a very basic introduction.